Okay, so let's look at the first question here. So a point mass m moves in a straight line under a retardation given by kv square, where k is a positive constant and v is the instantaneous velocity, so which means velocity at time t. The initial velocity of the point mass is u, and the displacement of the point. Okay, so you have to find the displacement of the mass at time t. So we have four options. So let's begin. Let me look at it. kv square. Okay, so we are told that we are given retardation, so this is nothing but negative acceleration. So we are given this, so you can write a, which is acceleration, as minus kv square. Since it is negative, since it's being told that it's a retardation, so we are using the negative sign, and we have to figure out the displacement. So we have to go from acceleration to displacement. So I'll denote displacement with x. So what do we know about the relation between displacement and acceleration? So we know that we have acceleration. Suppose we have displacement. Suppose, no, sorry, not displacement. Suppose that an object is at point x at any given time. So the rate of change of that object with respect to time is velocity. So if I do this, this is nothing but velocity, and the rate of change of velocity with respect to time is acceleration. So if you want to go from displacement to acceleration, we have to differentiate it twice. So similarly, if you want to go from acceleration to displacement, we have to do the opposite of differentiation, which is integration. So we first integrate, and we have to integrate it twice. So whatever the term is, we integrate it twice and we get the value of x. So right now we have a equals to this, so we have to integrate it twice, and then we'll reach the displacement. So how do we go about it? So let me just give it a general example. So if dv by dt is equals to a, that means this is a differential equation, variable separable. Technically speaking, this is a variable separable differential equation. This becomes dv equals to a dt, and if we integrate this, we get v equals to a times t. Now again, so we got this v equals to at. So now to get displacement, what we do here is dx, so yes, we don't need this, dx equals to v dt. Now since v equals to at, we will put at dt equals to dx, and then we integrate this, we get x times a t square by 2. So this is just the general example that I'm giving. This is how we have to approach. We have to integrate it twice. So let's start from this. Okay, again we have acceleration equal to minus kv square, and as I've just shown you before, acceleration can be written as dv by dt. So you can write this as dv by dt is equals to minus kv square. Now again, this is a variable separable differential equation, so we'll separate the variables. we'll bring all the v's to the left hand side. So we have dv by v square, and we'll take the dt to the right hand side along with the constant t. So this is what we have, and now we are going to integrate this, and this is a definite integral. So for right hand side, we're going to integrate from time t equal to 0 to time t equal to t, and the velocity at time t equal to 0, the initial velocity as given in the question, as you can see here, the initial velocity of the point mass is small u, and v is the instantaneous velocity, that is the velocity at any given time t. So the initial velocity is small u, and at any given time, so at capital T, the final velocity is v. So on the left hand side, we are going to integrate from u till v. Now let me start with the left hand side. So dv of this can be written as v to the power minus 2 by 2, and integration, it is very simple. The structure of this is of any integration is minus 2 plus 1 minus 2 plus 1. So this okay, and again from u to v. So this essentially becomes minus 2 plus 1 is v to the power minus 1, and minus 2 plus 1 is minus 1. So it's just minus of u to v. V to the power minus 1 is nothing but 1 by v, and you have to solve from u till v. So now if you expand this, the first term would be minus 1 by v plus minus 1 by u. So this is nothing but minus 1 by v plus 1 by u. So this is the left hand side. Now let's move on to the right hand side. The right hand side is very straightforward. Okay, so first of all, minus k is a constant, so we move it out. Then we integrate dt from 0 to t. So integration of dt is nothing but t, and we're going to integrate it from 0 to t. So it's k of t. Okay, let me just, for the sake of formality, let's just do it step by step. So from t to 0, so it comes out to be minus of kt. So this is minus of kt minus of kt. So this is what we have, but we are going to rearrange it now in terms of v, since we want to figure out the equation for velocity. Why? Because next we are going to integrate that equation of velocity so that we get the expression for displacement. So okay, I'm going to move the v this side and bring minus kt this side. So it turns out to be, should I do it left? Yeah, I'm going to do it step by step so that there is no confusion. So let me first take minus 1 by v to the right hand side. So this becomes 1 by u equals to minus k times t plus 1 by v. Now I'm going to move this kt to the right hand side, to the left hand side. So 1 by u plus kt equals to 1 by v. Now if you add this one, so u will be the common denominator, and we have to multiply this with ukt. equals to 1 by v. Now we have in it, so we have this equation in terms of 1 by v. So in order to get it in terms of v, we are simply going to flip the equation and bring this term to the left hand side, just for clarity. So v equals to u times 1 plus uk t. So this is the equation of velocity. So step 1 is done. Now we have to integrate this term one more time so that we get the expression for displacement. So displacement is, so we can write v as dx by dt. So I'm going to replace this here. So we can write dx by dt equals u1 plus ukt. Now again, this is a variable separable equation, so we have to take the dx. So there is no x on the right hand side, there is only one dx, so we'll keep the dx on the left hand side, and on the right hand side all the others are constant. The initial velocity is a constant, the k, the constant, is obviously a constant, and then we have time, that's the only variable. And so we are going to take the dt over here, so the right hand term becomes ukt times dt. So this is the term that we are going to integrate now. What do we get? Again, you have to remember that we are integrating from time 0 to t, and the displacement at time 0 is 0. That means it's at the initial position, and over time t it has moved a distance of x. So that's what we have to do this. So left hand side integrating is very simple, x from 0 to t. So this is nothing but x minus 0. This is equals to x. Left hand side is probably the easiest integration that you'll ever have to do. The right one though, this is tricky. How do we approach this? So the way we can go about this is by considering this scenario. So there is a special case of integrals where if we have an integral in the format f dash x, yes, divided by f of x. If you have an integral of this term, so this equals to natural log of fx plus c. So does this follow? Let us check. Okay, so if suppose fx is equals to 1 plus ukt, so if we differentiate this ddx of fx, this is nothing but f dash x. What would it look like? It will look like ddt of 1 plus ddt of ukt. Now the differentiation of a constant is 0, so this will be 0, and here uk is constant, so we'll bring uk to the left hand side, and we are remaining with dt times dt. So we cancel that, so our final term will be uk. This is the value of f dash x. But do we have uk here? Do we have uk? No, we only have u. So we do not exactly have this format, but we can make it in that format by making some modifications. So if we divide both the numerator and the denominator by k, so we haven't changed anything because the numerator and denominator can cancel itself. so we haven't changed anything. The equation is exactly the same, but with some rearrangement we can make it work. So what we have done in the first step is multiply and divide the right hand side with k. Now the numerator I'm going to move it inside. 1 by k times uk plus ukt dt. Now this term, now this thing is in this format, f dash x times fx, and since this is in that format, now you can use this which is natural log of fx, where fx is, what is fx? 1 plus ukt. So you can write the next step as 1 by k times natural log of fx, where fx, we're going to replace fx with this term, which becomes 1 by k times natural log of 1 plus ukt. So this is the value of, not exactly, now we'll also have to integrate it from 0 to t. Okay, so let's expand that. So x equals to 1 by k times log of 1 plus ukt, where this t is this t, minus log of 1 plus uk times 0. So replacing this one with this 0. So this becomes natural log of 1 plus ukt minus log of natural log of 1. Now what is natural log of 1? Natural log of 1 is equals to 0. So this term essentially becomes 0. So what we are left with is 1 by k times natural log of 1 plus ukt. So this is the expression for displacement. So this will be the displacement at time t. Now let's look at the option. Which option has this? If you look at option 1, that's the one that has this. We have 1 by k log of 1 plus kut. This is nothing but the same thing. Ukt, kut, you multiply it in any ways, any order, the value will be the same. So that's our answer, option A. Yeah, so we can rewrite this thing as x equals to 1 by k times natural log of 1 plus kut, because the order of multiplication doesn't matter. So that's our final answer, option A.